So I want to explain a little bit about computational model for cognition that I came up with a few years ago. Um, and it's sort of based on thinking about and looking at data on the evolution of behaviors in animals, right? So, like the most basic sorts of life kind of just things happen and they react to it, and things happen and they react to it. It's just, it's very systematic in that regard. It's kind of like physics, right? Like the chemistry is is dominating everything. It's very stimulus response sort of thing. But then by the time you get to like human language, it's not like that anymore. It's There's more going on, and we're at the point where with human language, we're at the point where unless the church Turing hypothesis, thesis, whatever you want to call it, is wrong, which would be surprising, human language is the most powerful sort of computational mechanism possible. So it's kind of interesting how you get from just stimulus response to the most powerful thing possible. And I went to university where everybody, well, no, not everybody, like, but kind of the bigwigs they were all very deeply Chomskyan. Several of them got their PhD like signed off on by Noam Chomsky himself, so they're definitely going to be singing his praises. Um, so I grew up familiar with that bullshit, and I established my own kind of pushbacks to those ideas. Um, it's not all like any religious doctrine. It's not all bullshit. It's not all wrong. There's definitely a kernel of yeah, that's how that works. But that doesn't justify all the rest of it, right? But that's always the problem. Like, yeah. Anyway, so I kind of came up with, thinking about it and some familiarity with programming and computer science and things like this. I have a degree in mathematics. I have a degree in linguistics. I taught myself to program. It's not the greatest in any of these by any stretch of the imagination, but familiar enough to get myself into serious trouble. Make some real big mistakes, right? Yeah, that's kind of where I'm at. So looking at this, I came up with kind of an idea for three basic sorts of mechanism that I think you could justify in evolutionary terms. And as far as I know, I'm kind of the only person who's really looked at this in this way. So I'm not basing it really on anybody else. It's kind of just me putting things together, all brand new. So, of course, it's gonna be wrong. I totally don't think that I'm right about all of this, but it's something to work from. If anybody gives a shit, probably nobody gives a shit. So whatever. But yeah, so the first mechanism. So I named them. There's three of them, and I gave them human names, and then later on I added a fourth one. But so there's three basic ones, and I gave them human names, kind of trying to explain it to somebody else, kind of anthropomorphize them, and on the spot just kind of made up this little quick story, and that I don't remember, and I couldn't remake at this point, but anthropomorphized them and gave them all like a personality based on the computational mechanism capabilities. And so the simplest one, the first one, the microbial, like basic life, microbial life, bacteria, archaea, that kind of stuff. But also the way the solar system works and any sort of mechanical or physical interaction, that sort of thing, is covered by Genevieve. So this is just stimulus response. That's it. Very simple, very easy to understand. It's like a doorknob. Turn the handle, the door can open. Don't turn the handle, the door can't open. It's that sort of a thing. Yeah, it's just a switch. Like you trigger it the right way, and it'll do something. But then it'll just kind of be in that new state until you trigger it and put it back into different. Like that's it. That simple. The second one, Eleanor. She is the complicated one. She is the one that I think runs most of the show for living things. She is, well, that's apart from like basic chemistry, biochemistry, and all that. Genevieve is definitely extremely present and powerful. She does a lot. But Eleanor, a very similar mechanism. And at a certain level, perhaps almost indistinguishable from Genevieve. But then at the other end, almost indistinguishable from the other one, the Turing complete one, Emily. So Eleanor is basically it's this same sort of on-off switch. This, like Genevieve is, input output. Very similar to that, except Eleanor is programmable. So this is going to be things. So like Genevieve is going to be things like instincts, but Genevieve or Eleanor is going to be things like recognition of the letter A. Like it's very fast. You don't think about it. You don't have to worry about it. You programmed it. What does this mean? That could mean several different things depending on, it could be a W, it could be a 3, it could be a number of things. But whatever, like your brain just instantly, like, I know what that is, right? What is Unix? Like, these things. What is the color orange? Like, well, that's probably Genevieve, except the name and the category of orange would be Eleanor, because you're trained on it, you learned it, but it's a very rapid. Once it's programmed, it's extremely rapid, and young animals are much better for the most part at training Genevieve or Eleanor. See, I don't even know what the fuck I'm talking about. That's how stupid this shit is. Eleanor. So like young animals, their brain is kind of focused on training Eleanor. All right, so learn these little things so that later on you can just react and hopefully react correctly very quickly. That's the gist of Eleanor. The thing is that this, as a basic sort of mechanism, has a considerable range of power. Right? It can be extremely simple, where it looks a lot like Genevieve. Like it's just so basic and simple that you can't really. You get philosophers saying, well, is this instinct or is this learned? We can't tell. And there's a lot of room there. There's a lot of things where that boundary is murky. But then on the other hand, you get, so like recognition of the letter A. That's almost Genevieve level. It's just like You have to practice it a bit, but once you got it, oh my god, it's stupid fast. But then you are able to compound that with recognition of words that contain the letter A. And then you're able to further compound that by recognition of like larger or slightly new words that contain those or parts of those words, and it can get complicated. And but we're still operating in Eleanor. and and Eleanor can be sort of dynamic. Uh, so it doesn't have to be necessarily like you program and it's set for the rest of your life, whereas like recognition of the letter A or your name or things like this, how to count. That's pretty much like you learn it once and as a kid and you're good. You have it for life. Eleanor can also just be aspects of working memory. So one thing to note: this is not intended to be a model of the mind. That's not what this is. What this is it's just a description of the basic sorts of computational mechanisms that are at play. Right? Because, Genevieve, you know, beta decay in the nucleus of an atom. That would be Genevieve. Right? That has nothing to do with minds. Right? It's just describing how an interaction occurs. So, there's going to be, obviously, in your working memory, that's different than your established memories that are handling your name and, things like that, your address, stuff like that. Yeah, and some of them can be reprogrammable. Like, you probably have some things that you kind of cycle through, right? Maybe like credit card numbers or phone numbers or something like that. Depending on how often you lose or break your phone, you might have to get a new number every 3 months or something. You're not going to be keeping track of all of those old ones because why? Some of them you might remember, but for the most part, like Eleanor is this mechanism. It doesn't really care if you remember all of it. It's not an issue. Yeah. So then we get into, so Eleanor has huge range of things, and it doesn't describe like a part of the brain, right? That's not what I'm trying to do here at all. It's there's going to be multiple parts of the brain that employ this sort of computational mechanism, and I think it's pretty clear that regardless of what parts of the brain are happening, thinking of your mind, like how you operate as a human being, thinking of your mind, Eleanor is going to manifest in multiple different ways, and they're not always very similar to each other. It's really just the computational complexity of what's happening. That's all I'm really looking at. And in a very coarse sort of way. Because we only have 3 levels here. Like, we're going all the way from finite state automata, which actually both Eleanor and Genevieve are, to like linear bounded automata, right? With nothing in between, right? Like, the difference between Genevieve and Eleanor is programmable, but they're both finite state automata. These are terms that I did not make up. They are it's technical jargon that is it's not they're not good names, but whatever. Yeah, so Eleanor and Genevieve, in a sense, are actually the same computational class. But I found it useful to distinguish them. And then you get Emily. So there's a big jump here. If you're familiar with like the Chomskyan hierarchy, I skipped, I think, 2 levels. They're not represented. It's fine. It's fine. You don't really need them. And I might get into touch on that at least a little bit. But so we kind of get up to the linear bounded automata. So that's I forget, type 0. I don't know. I can never remember which end is. There's a 0, 1, 2, and 3. But I can never remember if finite state automata is 0 or if, Turing completeness is 0. I don't remember which end is which. It doesn't really matter. Fuck it. You can look it up, and if you give a shit and you've made it 15 minutes, look it up. It's fine. Anyway, so yeah, Emily is the one that can handle Turing complete instruction sets. So not Turing complete because it has to be physically possible. The actual Turing completeness requires infinite time and infinite memory, and we clearly don't have that. We have finite time and finite memory, so a step below that, the physically realizable version of Turing completeness, linear bounded automaton. So this one, I kind of think in your mind, this was only represented once. Maybe not. It might be a little more distributed than that, but it seems to not really like to come out and play very much. Eleanor, for the most part, runs the show. She runs your life. She's in charge, for the most part. Emily, every once in a while, can kick in and say, hey, you fucking shit up. Let's fix this. Emily does come out to play quite a bit with language, but not really necessarily in every sentence or even every conversation that people have with each other. So this is kind of a place where I depart rather drastically, I think, based on my understanding of how everything works, with other models of language, cognition, because basically kind of everybody's out there looking for, what is the mechanism that controls language? And basically my take on it is that's the wrong way to look at this. It's not a single mechanism. You can look at language and say, okay, there has to be. It's a Turing complete instruction set, so there has to be a mechanism that can handle a Turing complete instruction set at play. But in most instances, it's actually not even engaged. For the most part, the way that human language is structured, we don't really use it. Which is very interesting because really every other animal, their communication systems also don't use it. Which is why I think in a previous, I've mentioned previously that language is human specific, and it's like the term language, when I use it, it means something very, very specific. And this is it. It has to be the Turing complete thing. Right, frogs definitely don't use it. They use probably only Genevieve. Birds, smarter birds at least, are going to be using Eleanor, at least to a degree. Especially like mockingbirds, right? They learn, they collect these little sounds, these little sound bites from all over the place, and then they put them on repeat. Usually triplicate, and then they go to something else, right? That's how you can tell it's a mockingbird, because you'll hear a little 2-3 second blip 3 times, and then it'll swap over to something else 3 times, and then it'll swap over to something else 3 times. Their voice is also very slightly distinctive, but the pattern is really how you can identify a mockingbird. Yeah, so they're listening and they're learning and they're programming their brain and remembering this, but the structure that they're mapping that onto is consistent across the species. It's not learned; it's instinctual. So the structure, that 3 3 3 3 3, that structure is Genevieve. It's built in somehow. But Eleanor is at play to bring in material to map onto the structure. Human language operates in a very similar sort of way. There are certainly aspects of it that are Genevieve. Um, like a lot of like emotional sorts of things and uh, yeah, like sorts of things that you do with your face and the inflection in your voice and that are really like span all of the languages. It's just like how humans are. And then there's aspects that are certainly Eleanor, so that's going to be like the sounds that you use, the phonology of your language. And it's going to be very hard for you. This is like low level Eleanor that's basically programmed once, and it's really hard to change that programming. So like you learn Australian English, and then you try to you come to America and you're trying to talk with an American accent, and it's difficult. Or you try to learn like Swahili or something, and it's very difficult. Or you try to learn Chinese, and it's absurdly difficult. The details of the pronunciation. You can certainly become comprehensible, but sounding like a native is probably not worth the effort. That's Eleanor at play right there. But then the things that'll really get you with learning a new language is going to be Emily. And a big part of that is because Emily in humans is not very powerful. This is a very okay. So like a way you can look at this is computers, right? Um, computers from 1976, an original Apple One, and your gaming computer today. They have the same computational complexity in an abstract sense, right? They can both handle Turing complete instruction sets, just like your brain, right? English is a Turing complete instruction set. Japanese is a Turing complete instruction set. COBOL is a Turing complete instruction set. In an abstract sense, these are all kind of on the same playing field. But clearly, your gaming computer today is significantly more powerful than an Apple One from 1976. So there is some level where, this extremely granular way of looking at it is missing something. And that one of that's something in terms of humans. We're extremely weak. We're capable of handling a Turing complete instruction set, but just barely. Especially quickly. We can only handle, something like 3 or 4 or 5 things at once that we can set something aside in memory and then come back to it and remember to come back to it. Once you build up that queue too big, you forget, right? It's like, okay, well, you start getting a fork to make something, and then somebody tells you got to do something, and then after 3 or 4 things, you start losing why are you holding a fork, right? Like, what the hell is... Like, everybody's had this sort of experience, right? You you're just juggling too many things and you can't keep track of it, and you look down and like, wait, where am I? What happened? Why is this here? Why am I holding this? Where's the thing that I was holding? Whatever. You lose track of it. And it only takes about 4 or 5 things all at once to cause that to happen. So as our Turing complete computation system is weak. It's not very good. But it is there, and it is technically capable of handling a Turing complete instruction set. And so, yeah. um, Interestingly, it is quite demonstrable that other animals might have slightly more powerful Turing complete mechanisms in their brains. They just don't employ it for their automatic communication between individuals. So something happened with humans where we brought that into the communication side, and that might have actually weakened it slightly. Like, for instance, chimpanzees, they're able to track something like 8 or 9 things all at once, whereas we can only track about 4 to 6, kind of at the outside, at the extreme outside 7. Like, if you're really focused, if you got like somebody who's really fucking good at this, 7 is like kind of the absolute limit. For most people, it's going to be around 3 or 4, maybe 5 if it's something they're very familiar with. It's very simple. But chimpanzees, they're good with 8, 9, 10. Right, so they're Q, and the aspect that makes it Turing complete is so we can put things into memory and then we can just kind of jump around. We don't have to process them in the order that they came in, right? So Eleanor and Genevieve, they process things as they come in, and you cannot change the order. You cannot set something aside and then come back to it. Emily can do that. Emily can set something aside and come back to it. Humans were only able to handle 4 or 5, something like that. It's not a hard limit. It's a little bit fuzzy what counts as a thing even, and you can sort of, if you, with a little bit of practice, especially and this is kind of what becoming like a professional in a field is, or like what training is supposed to do for you. You can, with something that you're very, very familiar with, you can actually kind of set things into more long-term sort of memory and pull that, right? But you're kind of not. Like, you're cheating, right? It's like, there's a routine for doing this. So really all you did is you know what the routine is, and you know where you are in the routine. You're kind of cheating by using more of an Eleanor side of the memory system to supplement Emily. And, that's what writing is. That's what all sorts of these other things are. They're ways that you can supplement the power of Emily so that you can handle a little bit more complicated tasks. I feel like I lost where I was going with that. Yes. So, right. So other animals definitely have it. Even things like mice, small animals, finches. They have it for sure. They just don't implement it in their communication system. We do. And really, as far as like Chomsky's like universal grammar, language is an instinct. That might be about as far as I would agree with that. Like, yeah, there's something happened with human cognition where Emily sort of switched roles and became more involved in our communication system, And that involvement is what gave us language. It's what made our communication system into language. Because without Emily, it couldn't be a Turing complete instruction set. Because by definition, the mechanism processing it wouldn't be capable of handling a Turing complete instruction set. So it couldn't be a Turing complete instruction set. It would be more like, HTML, right? Which is, if you're at all familiar with HTML, it's not Turing complete, right? It's, you have like an open bracket. This tells you, a letter or something that tells you what it is, what the following stuff is going to be. It does its stuff, and then close bracket, and then we move on to something completely different. There's no, like, we enter like a scope where, so like, this is going to be text or something, and then whatever, and then we end the text, and then we move on to something else. That's an Eleanor sort of thing. Eleanor Genevieve. It's in that territory. That's not Emily. That's, as far as like programming goes, Emily is going to be handling things like for and while loops, go-tos, which are implicit in those, stuff like that, where, or conditionals like if then, right? So you can skip around in the program text. You're not just reading it, right? Like an HTML code, the way that your web browser or whatever is reading it, at least traditionally, I think it's become, I don't even know, but like old school HTML, just HTML from the 90s, the web browser would just start reading from the top, do all of the things that it said, and there you go. It's like a recipe for making a cake. You just read the instructions, you do those things, and you're done. There's never we go back, and we go back, and we go back. Like in your video game, you clearly, it keeps drawing the background as you're walking. Like, it has to keep drawing the background, so it has to keep looping, right? Clearly. Otherwise, it would have just drawn it once, and you would have a picture. You wouldn't have an interactive video game. Right, so that sort of system where you can go back and handle, parse it again and maybe get a different outcome, and then go back and parse it again and get an even different outcome, and parse it again and get a different outcome, and based on the stimulus, that's Emily, that ability to go back. And as far as I think anybody has found, certainly the last time I checked, no animal communication system outside of human communication systems is capable of that. And the way that it manifests is generally with things like pronouns. We use it consistently with pronouns. So, like, okay, I saw it and it was broken. Something like that. Like, I saw the car and it was broken. Something like that. Alright, so that one, it's kind of more Genevieve side, but the car and it, like, it's kind of self-referential. A more clear example would be like, what are you talking about? Right? What? So some languages like Chinese would say, "You're talking about what?" Kind of as a general structure. There, you can definitely fuck around with stuff. You can move stuff to the front in Chinese, kind of depending on whatever. But it's kind of the most basic structure. You're talking about what? Right? Because, and if you were to say, I'm talking about the weather. Okay, so the weather and talking about go right next to each other. Right? This is the talking about opens a scope, the weather satisfies it, closes that scope. Stimulus, reaction. Boom. Eleanor. Or Genevieve. It's not Genevieve, it's programmable, so it's Eleanor. Right? So there is no syntax here. So this is syntax. When I say syntax, what I mean is a behavior that requires Emily. So there is no syntax here, in that sense. And consistently, like if you look at definitions of syntax, they almost always come back to they reduce down to what I'm saying, a mechanism that requires Emily. It's just that it's also systematically broader than that, and I think that that's needlessly confusing. So I just kind of like chopped off everything else and said, no, what syntax actually should mean. So the way that I'm going to use it is it should mean any pattern in a language that requires Emily. And that's it. So talk about the weather, there's no syntax there. We have a flicking of the switch, and then we have the light turning on. Finite state automata. No Turing completeness required. We turn the door handle, the door opens. But with what are you talking about? The what attaches to talking about. But now there's stuff in between it. So what has happened is, with what, we have opened a scope, and then we just kind of set it aside for a minute. And are you? Right? These words aren't... there is some things involving handling, maintaining, queuing that you need to be maintaining this. Just kind of set it aside and remember that we have this scope open. And what are the characteristics of this scope that is being handled with the are you, right? What are you talking about? But it's closed with talking about. So there's signal in there that we need to be listening to, while also keeping track of the what. This is Emily. Emily is absolutely necessary for this to happen. Because basically what we're doing is we are, in our mind, we're recording this conversation, a few seconds worth of conversation. What are you talking about? It's a short sentence. We can keep that. That's, probably a second and a half, something like that, and we can track something like 4 seconds, 3 seconds, somewhere in that ballpark. Maybe 5 on the outside. But a few seconds worth of speech we can handle, right? We can remember that. And we're just kind of always like maintaining this as a buffer. So this fits in there. And we're able to analyze this and say, okay, the what, that's an important thing that we're going to have to resolve its scope in a minute, but we're going to have to set that aside for right now and deal with the other stuff. There's some more signal coming that we have to handle. We have to process this separately. And then it's the what is going to get resolved with something after this part of the signal, the talking about, and then we have to bring it all back together. We have to, So, that juggling, that's Emily. That's syntax. And really consistently, when you look at the way that linguists talk about language, they've been saying this for centuries. They just haven't been saying it clearly. And consistently, you get a lot of people coming in and looking at the, talking about the weather and conflating that as syntax when it isn't. So, behaviorally, Other animals can demonstrate this. They just can't do it with their communication systems. And you can see this if you look at like transcripts of like Coco the gorilla or Nim Chimpsky or like any of those experiments where they try to teach an ape, a non-human ape, because humans are apes, but a non-human ape how to talk. They can learn the words, right? That's Eleanor. Totally fine with that. It's programmable, like, we can do that. No problem. Dogs can do that. Rabbits can do that. Birds can do that. You know. And we kind of get into this pissing contest about, oh, this animal can learn this many words, and this animal can learn this many words. And that's not really important. That's not what language is. Language isn't built on that. It's not unimportant, but it's not... That won't ever give you language. Sort of. There's some caveats to that one, but the way that it's thought of, no, it doesn't actually matter, really. Like, yeah, so like the gray parrot can have like 500 words, and the German Shepherd can have like 150 words. So like, I don't know what the numbers are, but it's some bullshit like that. And like the horse can remember 20 words, you know. And like you kind of get into this pissing contest of like, well, my research found that this sort of goldfish can learn this many words. Like, okay, like yeah, that's cool, but fuck it. But behaviorally, animals are able to demonstrate syntax. They just don't do it in their communication systems. And you see this in like chimpanzees and gorillas and orangutans all the time. If you look at their behaviors, they're absolutely demonstrating Turing-complete thought. But they are not capable of Turing-complete communication, which is amazing. And better than this, they are able to communicate Turing-complete thought without using Turing-complete communication. So this kind of turns the whole, like, thought gives birth to language sort of idea completely on its head. It's absolute and utter bullshit. No, it works exactly the opposite way. Language does not beget thought. Thought is there. Much more powerful than language from the outset, kind of all throughout your life. Language or thought is much, much, much more powerful. And it would have to be, like, really, if you think about it, of course it is. Because how would you learn a language if you required the language in order to learn things? Right? Like, you know, some Chomskyans like researching, what was her name? Anyway, that girl in California. They're like surprised when they're like, oh, well, she's able to talk about things that happened before she learned how to talk. Yeah, because her brain worked and she had thoughts. You would have to in order to learn how to talk. How could you possibly learn a word for something if you weren't able to experience that something before learning the word? You have to have the experience to tie the word to. What the fuck? Yeah, so no. I might have phrased it earlier incorrectly, but language does not give you thought. It does not give you the ability to think. So that is bullshit. Thinking in a Turing-complete manner also doesn't give you language. Language is just kind of this thing that has happened for us for whatever reason, and no other animal. They have communication systems, and there are varying levels of computational complexity in those systems, but only humans have language, as far as anybody's research has really demonstrated to this point. I would not be surprised if there are a few, particularly birds, that are capable of language, but as far as we can tell, they not. It's not obvious. Anyway, I definitely have more on this, but 45 minutes, pretty good time. So I'll end it there. I think the next one I'll talk about the fourth. Right, so we have Genevieve, Eleanor, Emily, and then there's a fourth one that I came up with to explain properly explain why Chomsky's wrong. So that'll be the next one.